Right now, 746 million miles away from Earth, there's a planet so massive that it could swallow over 760 Earths inside its volume. Yet so light that if you could somehow find an ocean large enough, Saturn would float like a giant cosmic beach ball. This isn't science fiction. It's one of the most mind-bending facts about our solar system. Saturn, with a diameter of 72,367 miles, is nearly 10 times wider than Earth, yet its average density is only 0.687 grams per cubic centimeter. Water has a density of 1.0 gram per cubic centimeter. This means Saturn is literally less dense than water. For centuries, we believed that larger planets must be heavier. That size and mass went hand in hand like they do with objects in our everyday experience. A larger rock is heavier than a smaller one. A bigger car weighs more than a smaller one. But Saturn shatters this intuitive understanding completely. Here's a world that dwarfs our planet in every dimension, yet composed of materials so light that the entire planet would bob on the surface of a cosmic ocean like a cork. The numbers are staggering. Saturn has a mass of 568 trillion kilograms. That's 95 times more massive than Earth. You'd think something 95 times more massive would sink instantly in water. But Saturn's S-volume is so enormous that when you divide its mass by its volume to calculate density, you get a result that challenges everything we thought we knew about how planets work. Saturn contains enough material to build 763 Earths. Yet all that material is spread out across such a vast volume that the average density becomes lower than the liquid we drink every day. Here is what makes this discovery deeply unsettling for our understanding of planetary science. Saturn isn't just slightly less dense than water, it is significantly less dense. If you could somehow slice Saturn into cubes and drop them into Earth's oceans, every piece would float with about 31% of its volume above the waterline. We're dealing with a planet that defies our most basic assumptions about how matter behaves when assembled on planetary scales. Scientists initially thought their calculations were wrong when they first determined Saturn's density in the 18th century. Christian Huygens, who discovered Saturn's rings in 1659, spent decades trying to understand how something so massive could be so light. The measurements seemed impossible. How could a planet larger than Jupiter's volume be only 1/3 as dense as our moon? The answer lies in Saturn's composition. But it's not a simple story. Saturn is composed primarily of hydrogen and helium, the two lightest elements in the universe. But here's where it gets truly bizarre. Even though hydrogen and helium are incredibly light, they recompressed under such enormous pressure inside Saturn that they exist in states of matter that don't occur anywhere on Earth. We're talking about metallic hydrogen, liquid helium at pressures millions of times greater than Earth's atmosphere, and gravitational compression effects that create density variations across Saturn's interior that span several orders of magnitude. Dr. Raddat, held from the University of Zurich, who studies planetary interiors, explains the paradox. Saturn teaches us that planets don't work like scaled-up versions of everyday objects. When you're dealing with masses equivalent to hundreds of Earths compressed into spheres tens of thousands of miles in diameter, the physics becomes so extreme that normal intuition breaks down completely. But Saturn's low density creates even more puzzling implications. If Saturn is less dense than water on average, what does that tell us about the internal structure? How can a planet maintain its spherical shape while being composed of materials lighter than water? The answer involves understanding pressure gradients, gravitational compression, and phase transitions of matter under extreme conditions that push the boundaries of physics. Tonight, we're diving deep into one of the solar system's most counterintuitive phenomena. You'll discover exactly how Saturn's internal structure creates such low density, learn why this has revolutionary implications for understanding planetary formation throughout the universe, and explore what would actually happen if we could perform the ultimate thought experiment, dropping Saturn into a cosmic ocean. We'll investigate the precise composition of Saturn's atmosphere and interior, examine how gravitational forces compress hydrogen and helium into exotic states of matter, and uncover the role that Saturn's spectacular ring system plays in our understanding of planetary density. You will learn about the spacecraft missions that have revolutionized our knowledge of gas giant planets and discover how Saturn's floating ability connects to fundamental questions about planetary formation and evolution. We'll explore the mathematical relationships that govern planetary density, investigate how Saturn compares to other gas giants in our solar system, and beyond, and examine what Saturn's unique properties reveal about the conditions that existed when our solar system was forming 4.6 billion years ago. You will understand how density measurements led to breakthrough discoveries about planetary interiors and why Saturn remains one of the most scientifically fascinating worlds in our cosmic neighborhood. This isn't just a story about a floating planet. This is about understanding how gravity, pressure, and composition interact on planetary scales to create worlds that challenge our most fundamental assumptions about how matter behaves. Saturn's ability to float in water reveals deep truths about planetary science, materials physics, and the incredible diversity of worlds that exist throughout our universe. The concept of a floating planet forces us to reconsider what we mean by solid and liquid when dealing with objects containing the mass of nearly 100 Earths. Saturn exists in a state that's neither fully solid nor liquid, but something between, a massive ball of compressed gas that somehow maintains planetary stability while remaining less dense than the water in Earth's oceans. As we explore Saturn's floating mystery, you will all discover how this seemingly impossible property actually makes perfect sense when you understand the extreme physics governing gas giant planets. The same principles that allow Saturn to float also explain how gas giants form, why they're found throughout the universe, and what their existence tells us about the fundamental processes that create planetary systems around other stars. If you're fascinated by planets that challenge our understanding of physics, subscribe and hit the thumbs up button. And here's a mind-bending question to consider. If Saturn could float in water, what would happen to its famous rings? Would they float too? Or would they sink and form a cosmic island around the floating planet? Comment below with your thoughts. I'll pin the most creative scientific reasoning. Now, let's begin our journey into the physics of floating planets, where we'll discover how Saturn became the cosmic cork of our solar system and what its incredible likeness reveals about the true nature of planetary worlds. Chapter 1. Density Discovery. The revelation that Saturn could float in water didn't emerge from modern space missions or sophisticated computer models. This mind-bending discovery was made over 300 years ago by astronomers armed with nothing more than telescopes, mathematical ingenuity, and careful observations of how Saturn's moons moved through space. Understanding how they determined Saturn's density reveals both the elegance of celestial mechanics and the shocking moment when humanity realized that planets could be fundamentally different from anything in our earthly experience. The story begins with Johannes Kepler's laws of planetary motion, established in the early 1600s. Kepler discovered that planets orbit the Sun in elliptical paths, with orbital periods that depend on their distance from the Sun. But it was Isaac Newton's law of universal gravitation, published in 1687, that provided the mathematical framework needed to determine planetary masses and, eventually, densities. Newton's gravitational law states that every object in the universe attracts every other object with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. This elegant equation meant that if you could measure how gravitational forces affect the motion of moons around planets, you could calculate the planet's mass with extraordinary precision. Saturn presented a perfect laboratory for testing these gravitational principles. The planet possesses numerous moons with well-defined orbital periods that could be observed and measured from Earth. Titan, Saturn's largest moon, orbits every 15.9 days at a distance of approximately 759,000 miles from Saturn's center. Using Newton's equations, astronomers could calculate that Saturn must contain a specific amount of mass to generate the gravitational force needed to keep Titan in its observed orbit. Dr. Giovanni Cassini, the Italian astronomer who discovered 4 of Saturn's moons between 1671 and 1684, was among the first to attempt calculating Saturn's mass using orbital mechanics. His observations of moon orbital periods, combined with careful measurements of their distances from Saturn, yielded mass estimates that seemed impossibly large. Saturn appeared to contain nearly 100 times more matter than Earth, yet telescopic observations suggested it was only about 9 times larger in diameter. The breakthrough came when astronomers realized they needed to account for Saturn's oblate shape. The planet is noticeably flattened at its poles due to rapid rotation. Saturn spins once every 10.7 hours, creating centrifugal forces that cause the planet to bulge outward at its equator. This flattening affects how Saturn's gravitational field influences its moons, requiring more sophisticated calculations to determine the planet's true mass. Christian Huygens, who discovered Saturn's largest moon Titan in 1655, spent decades refining mass calculations for the Saturn system. His work revealed that Saturn's mass was approximately 95.2 times that of Earth, while its volume was roughly 763 times larger. When Huygens calculated Saturn's average density by dividing mass by volume, he obtained a result that seemed to violate common sense: 0.687 grams per cubic centimeter. This density measurement meant that Saturn was less dense than water, which has a density of 1.0 gram per cubic centimeter. Huygens initially thought his calculations contained errors, but repeated observations and refinements of the mathematical techniques consistently yielded the same impossible result. Saturn, despite being nearly 100 times more massive than Earth, was light enough to float. The density discovery forced astronomers to confront fundamental questions about planetary composition. Earth has an average density of 5.52 grams per cubic centimeter because it is composed primarily of rock and metal. The Moon, made mostly of rock, has a density of 3.34 grams per cubic centimeter. But Saturn's density was lower than any solid material known to exist, suggesting that the planet must be composed primarily of substances much lighter than rock or metal. The realization that Saturn must be a gas giant rather than a rocky planet like Earth marked a revolution in planetary science. Astronomers began to understand that planets could be composed primarily of hydrogen and helium, the lightest elements in the universe, rather than the heavy rocks and metals that characterize terrestrial worlds. But understanding Saturn's composition raised new puzzles. If Saturn was made mostly of hydrogen and helium, why didn't it simply disperse into space like a gas cloud? The answer lay in understanding how gravity affects gases when they're concentrated into planet-sized masses. Saturn's enormous gravitational field compresses hydrogen and helium with such tremendous force that these light elements behave very differently from gases at Earth's atmospheric pressure. Dr. William Herschel, who discovered Uranus in 1781, conducted extensive observations of Saturn that confirmed its low density while revealing additional mysteries. Herschel's measurements showed that Saturn radiated more heat than it received from the Sun, suggesting that the planet was generating internal energy through gravitational compression. This finding provided crucial evidence that Saturn was actively compressing under its own gravity, creating the extreme pressures needed to maintain planetary structure despite its light composition. The density discovery also revealed why Saturn's spectacular ring system could exist. The rings are composed of countless ice and rock particles, each following its own orbit around Saturn according to Kepler's laws. But these ring particles can only maintain stable orbits if Saturn's gravitational field has very specific characteristics that depend directly on the planet's mass and internal structure. Saturn's low density creates a gravitational environment that's perfectly suited for maintaining complex ring systems over millions of years. Theoretical calculations in the 18th and 19th centuries revealed that Saturn's low density required a very specific internal structure. The planet couldn't be uniform in composition. It must have a denser core surrounded by progressively lighter layers of compressed hydrogen and helium. This layered structure results from gravitational settling, where heavier materials sink toward the center while lighter materials rise toward the surface. The mathematical elegance of Saturn's density calculation demonstrates how orbital mechanics can reveal the internal properties of worlds hundreds of millions of miles away. By measuring nothing more than the orbital periods and distances of Saturn's moons, astronomers could determine not just the planet's mass, but also make inferences about its internal composition and structure. Modern measurements using spacecraft data have refined Saturn's density to 0.687 grams per cubic centimeter, confirming the accuracy of calculations made centuries ago with ground-based telescopes. This precision validates both Newton's gravitational theory and the observational techniques developed by pioneering astronomers who first realized that planets could be fundamentally different from Earth. The density discovery established Saturn as the least dense planet in our solar system, but it also revealed that low-density gas giants might be common throughout the universe. As astronomers have discovered thousands of exoplanets orbiting other stars, they found many gas giants with densities even lower than Saturn's, suggesting that floating planets might be among the most common types of worlds in our galaxy. Dr. Heidi Hammel from the Space Science Institute reflects on the historical significance of Saturn's density discovery. The realization that Saturn could float in water represented one of the first major challenges to anthropocentric thinking about planets. It forced us to accept that worlds could be fundamentally different from Earth, opening our minds to the incredible diversity of planetary types that we now know exist throughout the universe. Understanding how Saturn's density was discovered reveals the power of mathematical physics to unveil hidden properties of cosmic objects. The same gravitational principles that allowed 17th century astronomers to determine that Saturn could float also govern the formation of planetary systems, the evolution of stars, and the large-scale structure of the universe itself. The density discovery transformed Saturn from a mysterious ringed object in the sky into a window for understanding how gravity, pressure, and composition interact to create planets with properties that seem to defy common sense. This revelation that a planet larger than Earth could be lighter than water opened the door to understanding gas giant planets as a distinct class of worlds with their own unique physics and evolutionary pathways. Chapter 2. Mass Deception. Saturn's ability to float in water represents one of the most counterintuitive examples of how mass and size relate in the cosmos. While Saturn contains 95 times more matter than Earth, its enormous volume means that all this mass is distributed across such a vast space that the average density drops below that of water. Understanding this mass deception requires unraveling the complex relationship between how much matter a planet contains versus how that matter is arranged in three-dimensional space. The fundamental confusion about Saturn's mass stems from our everyday experience with objects where size usually correlates directly with weight. A large rock weighs more than a small rock. A big car is heavier than a small car, and a tall person typically weighs more than a short person. This intuitive relationship between size and mass works perfectly for objects made from similar materials, but breaks down completely when dealing with objects composed of fundamentally different substances. Saturn's mass of 5.683 times yd kilograms represents an almost incomprehensible amount of matter. To put this in perspective, if you could somehow gather all the matter that makes up Saturn and compress it into spheres the size of bowling balls, you would need 1.2 times Ya bowling balls, a number so large that it exceeds the estimated number of atoms in the observable universe. Yet all this mass is distributed throughout a volume so enormous that the resulting density becomes less than liquid water. The volume calculation reveals the source of Saturn's density paradox. Saturn's equatorial radius measures approximately 60,268 kilometers, giving the planet a volume of roughly 8.27 times 1,014 cubic kilometers. This volume is 763 times larger than Earth's volume, meaning you could fit 763 Earth-sized spheres inside Saturn with room to spare. When Saturn's enormous mass is divided by its even more enormous volume, the resulting density explains why this massive world could float. Dr. Konstantin Batygin from the California Institute of Technology explains the mass-volume relationship. Saturn demonstrates that when you read dealing with planetary scale objects, the relationship between mass and volume becomes highly nonlinear. Small changes in composition can create dramatic differences in density, leading to planets that challenge our intuitive understanding of how matter behaves. The composition of Saturn's mass provides the key to understanding this density paradox. Approximately 96% of Saturn's mass consists of hydrogen and helium, the two lightest elements in the universe. Hydrogen has an atomic mass of 1, while helium has an atomic mass of 4. Compared to heavier elements like iron, atomic mass 56, or lead, atomic mass 207, that comprise much of Earth's mass. This means that Saturn's enormous mass is built from the lightest possible cosmic building blocks. But Saturn's low density isn't simply due to its light elemental composition. The planet's internal pressure creates exotic states of matter that don't exist anywhere on Earth, fundamentally altering how hydrogen and helium behave under extreme conditions. At the pressures found deep within Saturn, millions of times greater than Earth's atmospheric pressure, hydrogen transforms into a metallic state where it conducts electricity like copper or aluminum. This metallic hydrogen phase represents one of the most exotic forms of matter in the solar system. Under the crushing pressures inside Saturn, hydrogen atoms are squeezed so tightly together that their electrons become delocalized, creating a liquid metal with properties unlike anything found in terrestrial environments. Despite this extreme compression, metallic hydrogen remains significantly less dense than the rock and iron that comprise Earth's interior. The pressure gradient inside Saturn creates a complex internal structure where density increases dramatically from the outer atmosphere toward the core. Saturn's uppermost atmosphere has a density of only 0.001 grams per cubic centimeter to 10,000 times less dense than water. But at the planet's center, pressures may compress matter to densities exceeding 20 grams per cubic centimeter, approaching the density of platinum or gold. This extreme density variation means that Saturn's density of 0.687 grams per cubic centimeter represents a mathematical average across regions that span 5 orders of magnitude in actual density. The outer layers are so light they're almost vacuum-like, while the inner core may be denser than any material found on Earth's surface. The floating ability results from the fact that the low-density outer layers dominate the volume calculation. Modern computer models of Saturn's interior structure reveal how gravitational compression affects the distribution of matter throughout the planet. These simulations show that approximately 60% of Saturn's mass is contained in the outer 80% of its radius, where hydrogen and helium remain in relatively low-density gaseous and liquid states. The remaining 40% of the mass is compressed into the inner 20% of the radius, where extreme pressures create much higher densities. The gravitational forces responsible for creating Saturn's internal pressure gradients also explain why the planet maintains its spherical shape despite being less dense than water. Saturn's enormous mass generates gravitational acceleration of 10.44 meters per second squared at its surface, slightly higher than Earth's gravity, despite the planet's much lower density. This strong gravitational field prevents the light hydrogen and helium from escaping to space, while maintaining the pressure needed to keep the planet coherent. Saturn's rapid rotation adds another layer of complexity to its mass distribution. The planet spins once every 10.7 hours, creating centrifugal forces that cause Saturn to bulge outward at its equator. This obliqueness means that Saturn's equatorial diameter is 9% larger than its polar diameter, creating a significant deviation from perfect spherical symmetry. The rotational flattening affects how Saturn's mass is distributed in three-dimensional space, contributing to the overall density calculation. The role of Saturn's core in the mass deception remains one of the most intriguing aspects of the planet's structure. Theoretical models suggest that Saturn may contain a rocky core with a mass 10 to 20 times that of Earth, composed of rock, ice, and possibly iron. This dense core would have a density of 5 to 10 grams per cubic centimeter, similar to terrestrial planets. But this heavy core represents less than 25% of Saturn's total mass and occupies less than 5% of its volume, having minimal impact on the planet's average density. The discovery of Saturn's low density through careful mass and volume calculations represents one of the first major challenges to geocentric thinking about planetary formation. Early planetary formation theories assumed that all planets formed through the accretion of rocky material similar to Earth. Saturn's density measurements forced scientists to develop new theories about how gas giant planets could capture and retain massive hydrogen and helium atmospheres. Comparative analysis with other planets reveals that Saturn's extreme low density is unique in our solar system. Jupiter, despite being composed of similar materials, has a density of 1.33 grams per cubic centimeter due to its larger mass, which creates stronger gravitational compression. Uranus and Neptune, often called ice giants, have densities of 1.27 and 1.64 grams per cubic centimeter respectively, because they contain higher proportions of water, methane, and ammonia ices. The mass deception that allows Saturn to float also provides crucial insights into planetary formation processes that occurred 4.6 billion years ago. Saturn's ability to capture and retain such a massive hydrogen and helium envelope suggests that it formed early in solar system history, when the protoplanetary disk still contained abundant light elements. Planets that formed later, after stellar winds had dispersed much of the hydrogen and helium, could not achieve such low densities. Modern spacecraft missions have refined our understanding of Saturn's mass distribution through precise gravitational measurements. The Cassini spacecraft, which orbited Saturn from 2004 to 2017, used radio tracking to map Saturn's gravitational field with unprecedented accuracy. These measurements revealed subtle variations in Saturn's internal structure that affect how the planet's enormous mass is distributed throughout its interior. The implications of Saturn's mass deception extend far beyond our solar system. As astronomers discover exoplanets around other stars, they find that low-density gas giants like Saturn may be among the most common types of planets in the universe. Some exoplanets have been discovered with densities even lower than Saturn's, including worlds that would float even more readily than Saturn if cosmic oceans existed. Dr. Doug Lin from the University of California, Santa Cruz, reflects on Saturn's significance. Saturn's low density teaches us that planets can be built from radically different materials than Earth. This diversity in planetary composition suggests that the universe contains an extraordinary variety of world types, many of which would seem impossible based on our limited terrestrial experience. The mass deception that makes Saturn's floating ability possible demonstrates how gravitational physics can create planetary structures that seem to violate common sense. Saturn's enormous mass generates the gravitational forces needed to retain a massive atmosphere, while its light composition and enormous volume keep the average density low enough for the planet to float. This delicate balance between mass, volume, and composition represents one of the most elegant examples of how fundamental physics creates cosmic phenomena that challenge human intuition about how matter behaves on planetary scales. Understanding Saturn's mass deception reveals the universe as a place where size and weight relationships can be fundamentally different from everyday experience, where massive objects can be lighter than water, and where the physics of planetary formation creates worlds that expand our understanding of what is possible in the cosmos. Chapter 3. Hydrogen Ocean. Saturn's ability to float in water stems directly from its composition as a vast ocean of hydrogen and helium, the two lightest elements in the universe. Calling Saturn a gas giant oversimplifies the complex reality of how these light elements behave when compressed under the enormous pressures found inside a planet 95 times more massive than Earth. Understanding Saturn's ocean reveals a world where familiar elements exist in exotic states that create one of the most unusual planetary environments in our solar system. Hydrogen comprises approximately 96% of Saturn's atmosphere by mass, with helium making up most of the remaining 4%. Trace amounts of methane, ammonia, and other compounds contribute less than 0.1% to the planet's total composition. This means that Saturn is essentially a gigantic ball of compressed hydrogen and helium, held together by its own gravity and compressed into density regimes that range from nearly perfect vacuum to metallic states denser than terrestrial rocks. The hydrogen that dominates Saturn's composition exists in multiple distinct phases throughout the planet's interior, each with dramatically different properties. In the outermost atmosphere, hydrogen behaves as a conventional gas with densities similar to Earth's upper atmosphere. But as pressure increases with depth, hydrogen undergoes phase transitions that transform it into liquid, metallic, and possibly even solid forms that don't exist under any conditions found on Earth. Dr. Burkhard Mulitzer from the University of California, Berkeley, who models planetary interiors, explains the complexity. Saturn's hydrogen ocean spans physical conditions from the near vacuum of its upper atmosphere to pressures and temperatures that exceed those found in the Earth's core. Understanding how hydrogen behaves across this enormous range of conditions is one of the greatest challenges in planetary science. The transition from gaseous to liquid hydrogen occurs gradually as pressure increases with depth inside Saturn. Unlike the sharp boiling point that characterizes water's transition from liquid to gas at Earth's surface pressure, hydrogen's transition under Saturn's extreme pressures creates a gradual change from gas to liquid across a region thousands of kilometers thick. This means there is no definite surface where Saturn's atmosphere ends and a liquid ocean begins. Laboratory experiments attempting to replicate the conditions inside Saturn have revealed that hydrogen under extreme pressure behaves in ways that challenge fundamental assumptions about how matter works. At pressures exceeding 1 million Earth atmospheres, hydrogen transforms into a metallic phase where it conducts electricity like copper or silver, despite being composed of the lightest element in the universe. This metallic hydrogen phase represents one of the most exotic states of matter in the solar system. The transformation occurs when hydrogen atoms are squeezed so tightly together that their electrons become delocalized, forming a sea of free electrons that can conduct electric current. Theoretical calculations suggest that metallic hydrogen may be one of the most efficient electrical conductors known, potentially exceeding even the conductivity of silver or copper. The existence of metallic hydrogen inside Saturn has profound implications for understanding the planet's magnetic field. Saturn possesses one of the most unusual magnetic fields in the solar system. It is almost perfectly aligned with the planet's rotation axis, showing less than 1 degree of tilt. This precise alignment suggests that Saturn's magnetic field is generated through mechanisms different from those operating inside Earth or Jupiter. Computer simulations of Saturn's interior structure indicate that the metallic hydrogen region extends from approximately 30,000 kilometers depth to near the planet's center. This vast ocean of liquid metal generates electrical currents through convective motion driven by Saturn's internal heat, creating the dynamo effect responsible for the planet's magnetic field. The precise alignment of this field suggests that the metallic hydrogen region has a very specific structure and circulation pattern. The pressure required to create metallic hydrogen is so extreme that it can only be achieved naturally inside the largest planets. Jupiter also contains metallic hydrogen, but Saturn's lower mass means that this exotic phase begins at greater depths than in Jupiter's interior. This difference in metallic hydrogen distribution helps explain why Saturn and Jupiter have different magnetic field structures despite their similar compositions. Temperature plays a crucial role in determining how hydrogen behaves throughout Saturn's interior. The planet's upper atmosphere maintains temperatures around -180 degrees Celsius, cold enough that methane and ammonia can exist as solid crystals suspended in the hydrogen-helium mixture. But temperatures increase dramatically with depth due to gravitational compression, reaching an estimated 11,700 degrees Celsius at Saturn's center, nearly twice as hot as the Sun's surface. These extreme temperatures are generated primarily through gravitational compression rather than nuclear fusion. As hydrogen and helium fall towards Saturn's center under the influence of gravity, gravitational potential energy converts to thermal energy, heating the interior to temperatures that exceed those found in stellar cores. This internal heat generation explains why Saturn radiates 2.5 times more energy than it receives from the Sun. The combination of extreme pressure and temperature inside Saturn creates hydrogen density variations that span several orders of magnitude. At the planet's surface, hydrogen density approaches 0.001 grams per cubic centimeter, making it 10,000 times less dense than water. But in the metallic hydrogen regions near Saturn's core, densities may exceed 4 grams per cubic centimeter, approaching the density of diamond. Phase diagrams for hydrogen under Saturn's conditions reveal a complex landscape of different states that do not conform to simple solid-liquid-gas classifications. The hydrogen ocean inside Saturn may include supercritical phases where the distinction between liquid and gas becomes meaningless, superionic phases where hydrogen ions move freely through a lattice of electrons, and possibly even quantum phases, where hydrogen exhibits properties governed by quantum mechanical effects rather than classical thermodynamics. Recent theoretical work suggests that Saturn's hydrogen ocean may contain precipitation of exotic materials that don't exist on Earth. Under the extreme conditions in Saturn's deep interior, carbon and hydrogen may combine to form diamond particles that rain through the metallic hydrogen layers like crystalline snow. These diamond precipitation processes could affect Saturn's internal heat transport and contribute to the planet's unusual thermal properties. The helium component of Saturn's composition adds another layer of complexity to the planetary structure. Helium has different solubility properties than hydrogen under extreme pressure, leading to helium raining out of solution in certain pressure regimes. This helium precipitation creates compositional gradients throughout Saturn's interior that affect the planet's density distribution and thermal evolution. Spectroscopic observations of Saturn's atmosphere reveal trace amounts of water vapor, methane, and ammonia that provide clues about the planet's formation history. These heavier compounds likely originated from planetesimal impacts during Saturn's early formation, when rocky and icy bodies were incorporated into the growing planet. The presence of these materials in Saturn's hydrogen ocean suggests that even gas giants contain some rocky and icy components mixed throughout their interiors. The dynamics of Saturn's ocean create atmospheric phenomena that dwarf anything found on Earth. Convective currents driven by internal heating generate wind systems that persist for decades or centuries, creating the banded structure visible in Saturn's atmosphere. These circulation patterns transport heat from Saturn's interior to space, while maintaining the complex chemistry that creates the planet's distinctive golden color. Understanding Saturn's hydrogen ocean has revolutionized our knowledge of how gas giant planets form and evolve. The massive hydrogen and helium envelopes of planets like Saturn can only be captured during the early phases of planetary formation, when protoplanetary disks still contain abundant light elements. This suggests that gas giants like Saturn formed rapidly, accumulating their massive atmospheres before stellar winds dispersed the hydrogen and helium from the inner solar system. The hydrogen ocean that makes Saturn light enough to float also explains why gas giant planets are among the most common types of worlds found around other stars. The same physical processes that created Saturn's low-density structure operate throughout the universe, suggesting that floating planets may be widespread cosmic phenomena rather than rare curiosities. Dr. Jonathan Fortney from the University of California, Santa Cruz, reflects on the significance of Saturn ocean. Saturn represents nature's most successful experiment in creating a low-density planet. The hydrogen ocean that dominates Saturn's structure demonstrates how gravity can organize the lightest elements in the universe into stable, planetary systems that persist for billions of years. The hydrogen ocean that comprises most of Saturn's gas creates a planetary environment unlike anything else in our solar system, where the lightest elements in the universe are compressed into exotic states that challenge our understanding of matter while maintaining the low average density that allows this massive world to float like a cosmic cork in the ocean of space. Chapter 4. Rocky Heart. Deep beneath Saturn's vast hydrogen ocean lies one of the solar system's most mysterious features, a rocky core that may contain more solid material than Earth, Mars, and Venus combined, yet accounts for less than 20% of Saturn's total mass. Understanding this rocky heart reveals how Saturn maintains its structural integrity while remaining light enough to float, and provides crucial clues about how gas giant planets form from the collision and accumulation of smaller rocky bodies. The existence of Saturn's core was first predicted through theoretical calculations in the mid-20th century, when scientists realized that gas giant planets couldn't form through direct gravitational collapse of hydrogen and helium. These light elements don't condense into solid particles at the temperatures found in planetary formation regions, making it impossible for them to stick together through normal accretion processes. Instead, gas giants must form through a two-stage process, first building a substantial rocky core, then capturing massive gaseous envelopes. Saturn's core formation began approximately 4.6 billion years ago in the cold outer regions of our protoplanetary disk, where water, methane, and ammonia could freeze into solid ice particles. These icy particles, along with rocky dust and metal grains, gradually accumulated through gravitational attraction to form increasingly massive objects called planetesimals. As these planetesimals collided and merged, they built progressively larger bodies that eventually became massive enough to capture hydrogen and helium from the surrounding nebula. Dr. Jack Lesauer from NASA's Ames Research Center, who studies planetary formation, explains the core accretion model. Saturn's core had to reach approximately 1015 Earth masses before it could begin capturing significant amounts of hydrogen and helium. This critical mass threshold creates gravitational fields strong enough to retain light elements against the thermal motion that would otherwise cause them to escape to space. The composition of Saturn's core remains one of the most challenging problems in planetary science because it is buried beneath thousands of kilometers of compressed hydrogen and helium that prevent direct observation. Theoretical models suggest the core consists primarily of rock, ice, and possibly iron, with temperatures reaching 11,700 degrees Celsius. nearly twice as hot as the Sun's surface. At these temperatures, traditional distinctions between rock and ice become meaningless, as all materials exist in exotic high-pressure phases. Computer simulations of Saturn's interior structure indicate that the core may have a mass between 10 and 20 Earth masses, distributed across a region roughly the size of Earth, but with densities approaching 10 to 20 grams per cubic centimeter. This extreme density results from gravitational compression under the weight of Saturn's entire hydrogen-helium envelope, creating pressures millions of times greater than anything found on Earth's surface. Recent gravitational measurements from the Cassini spacecraft have provided new insights into Saturn's core structure by detecting subtle variations in the planet's gravitational field. These measurements suggest that Saturn's core may not be a simple spherical object, but rather a complex structure with varying density and possibly even a fuzzy boundary where core material gradually transitions into the surrounding metallic hydrogen. The fuzzy core model proposes that Saturn's rocky heart isn't sharply separated from its gaseous envelope, but instead consists of a gradient zone where rock, ice, and metallic hydrogen exist in a complex mixture. This structure could result from convective mixing processes that transport core material upward into the metallic hydrogen region, creating a transition zone hundreds of kilometers thick where solid and liquid phases coexist. Dr. Revin, held from the University of Zurich, who studies planetary interiors, describes the implications. If Saturn's core is indeed fuzzy rather than distinct, it suggests that the interior structure of gas giants is far more complex than we previously imagined. The boundary between core and envelope may be a gradual transition, rather than a sharp interface. The thermal evolution of Saturn's core plays a crucial role in understanding why the planet radiates more heat than it receives from the Sun. Gravitational compression of core materials continues to generate heat billions of years after Saturn's formation, contributing to the internal energy that powers the planet's atmospheric circulation and maintains its expanded size. Without this internal heating, Saturn would contract under its own gravity, increasing its density and losing its ability to float. Seismic studies of Saturn's core using data from atmospheric oscillations have revealed that the rocky heart may be partially molten, with liquid iron and rock phases coexisting under the extreme pressure and temperature conditions. These liquid phases could create convective circulation within the core that contributes to Saturn's magnetic field generation, working in conjunction with the metallic hydrogen dynamo to produce the planet's unusual magnetic properties. The formation history of Saturn's core provides insights into the early solar system environment when planets were assembling from smaller building blocks. Isotopic analysis of Saturn's atmospheric composition suggests that the planet incorporated significant amounts of material from the outer regions of the protoplanetary disk, where temperatures were cold enough for volatile compounds like water and ammonia to exist as solid ice. The timing of Saturn's core formation relative to Jupiter's development may explain why Saturn has a lower mass despite forming in a region with abundant solid material. Computer models suggest that Jupiter's rapid growth may have gravitationally scattered many planetesimals out of the region where Saturn was forming, limiting the amount of solid material available for Saturn's core accretion process. Impact processes during core formation likely delivered significant amounts of water to Saturn's interior, creating the water-ice component that theoretical models suggest comprises 30 to 50% of the core's mass. This water exists in exotic high-pressure phases that don't occur naturally on Earth, including superionic ice, where oxygen atoms form a crystal lattice, while hydrogen atoms move freely like a liquid. The density contrast between Saturn's rocky core and its hydrogen-helium envelope creates the extreme internal pressure gradients that compress both components into exotic states. The core's high density generates gravitational fields strong enough to compress the overlying hydrogen and helium to densities approaching those of liquid metals. while the core itself is compressed to densities exceeding those found in Earth's interior. Recent theoretical work suggests that Saturn's core may undergo slow convective overturn processes that mix core material with the surrounding metallic hydrogen over timescales of millions of years. These mixing processes could explain observed variations in Saturn's atmospheric composition and provide mechanisms for transporting rocky material throughout the planet's interior. The role of Saturn's core in maintaining planetary structure extends beyond simple gravitational binding. The core's thermal properties affect how heat flows through Saturn's interior, influencing atmospheric circulation patterns and possibly affecting the formation and evolution of Saturn's ring system. Changes in core temperature could alter Saturn's radius and density distribution, demonstrating how the hidden rocky heart influences observable planetary properties. The magnetic field generated by Saturn's core region may interact with the metallic hydrogen dynamo to create the planet's remarkably precise magnetic field alignment. Some theoretical models propose that the core acts as a magnetic anchor that stabilizes field generation in the metallic hydrogen region, explaining why Saturn's magnetic field shows less variation than Jupiter's more chaotic magnetic environment. Future missions to Saturn may use advanced gravitational sensing techniques to probe the detailed structure of the planet's core without requiring direct sampling. These measurements could reveal whether the core is solid or partially molten, determine its exact composition, and map how core properties vary with depth beneath the hydrogen ocean. Dr. David Stevenson from the California Institute of Technology reflects on Saturn's core significance. The rocky heart buried deep inside Saturn represents a fossil of planetary formation, preserving information about the materials and processes that built gas giant planets 4.6 billion years ago. Understanding this hidden world provides crucial insights into how planetary systems form throughout the universe. The rocky heart that anchors Saturn's structure demonstrates how solid material can be hidden within low-density planetary envelopes, creating worlds that appear to be primarily gaseous but actually contain substantial amounts of rock and ice compressed into exotic states. This hidden density helps explain how Saturn maintains its structural integrity while remaining light enough to float, revealing the complex internal architecture that makes floating planets possible. Chapter 5. Ring Paradox. Saturn's spectacular ring system creates a fascinating paradox when considering the planet's ability to float in water. While the rings appear massive and substantial in images, they contribute virtually nothing to Saturn's overall density calculation, despite spanning a diameter larger than the distance from Earth to the Moon. Understanding this ring paradox reveals how appearances can be deceiving on planetary scales and demonstrates the incredible thinness and low mass of one of the solar system's most beautiful features. Saturn's rings extend from approximately 7,000 kilometers to 80,000 kilometers above the planet's cloud tops, creating a disk structure with a diameter of 273,000 kilometers, over 170,000 miles. If you could somehow flatten Saturn's rings and place them between Earth and the Moon, they would span 2/3 of the distance between the two worlds. Yet despite this enormous spatial extent, the rings contain less material than a single small moon. The total mass of Saturn's ring system is estimated at approximately 1.5 times 1,019 kilograms, which sounds enormous until compared to planetary scales. Saturn's rings contain roughly the same amount of material as Saturn's moon mass, which has a diameter of only 396 kilometers. This means that if you could gather all the ring material into a single sphere, it would be smaller than most US states, yet spread across a disk larger than the orbit of Earth's moon. Dr. Larry Esposito from the University of Colorado, who has studied Saturn's rings for decades, explains the mass paradox. Saturn's rings are the ultimate example of how something can appear substantial while being almost insubstantial. The rings look impressive, because they're spread across such an enormous area. But their total mass is less than 1/10,000,000th of Saturn's total mass. The rings' negligible contribution to Saturn's density stems from their incredible thinness. While the ring system spans hundreds of thousands of kilometers in diameter, it's typically less than 1 kilometer thick, and in many regions, less than 100 meters thick. This creates a thickness-to-diameter ratio of approximately 1 to 300,000, making Saturn S rings proportionally thinner than a sheet of paper scaled to the size of a football field. The individual particles that comprise Saturn S rings range in size from tiny dust grains smaller than cigarette smoke to house-sized boulders, but the vast majority consist of ice chunks roughly the size of snowballs to small cars. These particles orbit Saturn independently, each following its own elliptical path according to Kepler's laws of orbital mechanics. The ring structure emerges from the collective motion of billions of individual particles, each responding to Saturn's gravity and mutual gravitational interactions. The composition of Saturn's rings further explains their low contribution to planetary density. Spectroscopic analysis reveals that the rings consist of 95 to 99% water ice, with small amounts of rocky material providing the slight coloration visible in high-resolution images. Water ice has a density of approximately 0.92 grams per cubic centimeter, which is already less dense than liquid water. When this ice is distributed across the enormous volume of the ring system, the average density becomes infinitesimally small. Theoretical calculations of ring particle distribution show that even within the main ring regions, the average density is less than 0.0001 grams per cubic centimeter, over 1 million times less dense than air at Earth's surface. This means that if you could somehow travel through Saturn's rings, you would experience an environment closer to interplanetary space than to any conventional material medium. The gravitational influence of Saturn's rings on the planet's overall mass distribution is so small that it doesn't measurably affect calculations of Saturn's density. Even if Saturn's rings were completely removed, the planet's density would change by less than 1 part in 10 million, a difference too small to detect with current measurement techniques. However, the rings do play an important role in understanding Saturn's rotational dynamics, which indirectly affects density calculations. The rings interact with Saturn's magnetic field through electromagnetic forces that create subtle torques on the planet's rotation. These interactions help determine Saturn's precise rotation period, which is crucial for calculating the planet's oblateness and its effects on internal pressure distribution. The age and origin of Saturn's rings remain active areas of research that connect to broader questions about planetary system evolution. Some theories suggest that the rings are relatively young features, perhaps only 10 to 100 million years old, formed by the tidal disruption of a moon that wandered too close to Saturn. Other models propose that the rings are ancient features that have persisted since Saturn's formation 4.6 billion years ago. The youthful ring hypothesis has important implications for understanding Saturn's density evolution over time. If the rings are young, then Saturn's current density represents its long-term stable value, unaffected by recent ring formation processes. But if the rings formed recently through moon destruction, Saturn may have been slightly more massive in the past, though the density difference would still be negligible. Cassini spacecraft observations revealed that Saturn's S-rings are actively losing mass through several mechanisms that affect their long-term evolution. Ring particles constantly collide with each other, creating dust that either falls into Saturn's atmosphere or escapes to space. Additionally, electromagnetic interactions between the rings and Saturn's atmosphere create ring rain that deposits ring material into Saturn's upper atmosphere at rates of thousands of kilograms per second. This ring mass loss process operates on timescales of 10 to 100 million years, suggesting that Saturn's current ring system may be a temporary feature that will eventually disappear entirely. As the rings lose mass over time, Saturn's total mass decreases slightly, but the effect on density remains negligible because ring mass is so small compared to planetary mass. The ring paradox extends to other aspects of Saturn's appearance versus reality. The rings appear bright and substantial in photographs because ice particles efficiently reflect sunlight, creating high contrast against the darkness of space. But this high reflectivity doesn't indicate high mass. It simply demonstrates that ice is an excellent reflector of visible light. The gravitational effects of Saturn's rings on spacecraft trajectories provide the most precise measurements of ring mass. The Cassini spacecraft's orbital mechanics were sensitive to gravitational perturbations from ring material, allowing scientists to determine ring masses with unprecedented accuracy. These measurements confirm that the rings contribute virtually nothing to Saturn's overall gravitational field. The ring system's influence on Saturn's atmospheric dynamics creates indirect effects that are more significant than the ring's direct gravitational contribution. Ring particles absorb and reflect sunlight in ways that affect Saturn's thermal balance, influencing atmospheric circulation patterns and potentially affecting the planet's overall heat distribution. These thermal effects could theoretically influence Saturn's atmospheric density distribution, though the impacts remain too small to measure directly. Future evolution of Saturn's ring system may actually increase the planet's density slightly as ring material continues to fall into Saturn's atmosphere. However, even if all ring material were incorporated into Saturn's atmosphere, the density increase would be immeasurable because ring mass represents such a tiny fraction of planetary mass. The ring paradox demonstrates how cosmic-scale phenomena can appear impressive while being physically insignificant in terms of mass and density. Saturn's rings represent one of nature's most beautiful examples of how gravity can organize small amounts of material into spectacular, large-scale structures that captivate human imagination while contributing virtually nothing to fundamental planetary properties. Dr. Carolyn Porco, former leader of Cassini's imaging team, reflects on the ring paradox. Saturn's rings teach us that cosmic beauty doesn't require cosmic mass. Some of the most spectacular phenomena in the universe emerge from the elegant organization of relatively small amounts of material distributed across vast scales. The ring paradox reveals that Saturn's floating ability depends entirely on the planet's internal structure rather than its external ring system. The rings serve as a gorgeous but gravitationally irrelevant decoration that has no measurable impact on whether Saturn could float in a cosmic ocean, demonstrating how the most visually prominent features of a world may be completely unrelated to its most fundamental physical properties. Understanding the ring paradox helps clarify that Saturn's low density emerges from its hydrogen-helium composition and internal structure, rather than from any effect of the ring system, confirming that the planet's floating ability is an intrinsic property of gas giant architecture, rather than a consequence of external orbital debris. Chapter 6. Formation Story. The story of how Saturn became light enough to float in water begins 4.6 billion years ago in the swirling disk of gas and dust that surrounded our young sun. Saturn's formation required a precise sequence of events that allowed the planet to capture and retain a massive envelope of hydrogen and helium, while maintaining the low density that would eventually make it the least dense planet in our solar system. Understanding this formation story reveals why floating planets like Saturn exist and how the early solar system created such diverse world types. The protoplanetary disk that gave birth to Saturn contained all the raw materials needed to build planets. But these materials were distributed in specific zones based on temperature and pressure conditions. In the inner solar system, close to the hot young sun, only rock and metal could exist in solid form. But in the outer regions where Saturn formed, temperatures were cold enough for water, methane, and ammonia to freeze into solid ice particles that could stick together through gravitational attraction. This temperature-dependent distribution of materials created what planetary scientists call the snow line, a boundary roughly 2.7 astronomical units from the Sun between Mars and Jupiter, where water vapor condenses into ice. Beyond the snow line, the available solid material for planet formation increased dramatically because ice represents a major component of cosmic material. This abundance of solid building blocks in the outer solar system made it possible for planets like Saturn to grow large enough to capture massive gaseous atmospheres. Dr. Alessandro Morbidelli from the Observatoire de la Côte d'Azur, who studies planetary formation, explains the critical role of the snow line. The increased solid material beyond the ice line allowed planets like Saturn to grow rapidly enough to capture hydrogen and helium before these light elements were blown away by solar winds. Without this abundance of ice, gas giant formation would have been impossible. Saturn's formation began with the gravitational collapse of a dense region within the protoplanetary disk, creating a concentration of solid particles that gradually accumulated into larger and larger objects. These planetesimals, ranging in size from kilometers to hundreds of kilometers in diameter, collided and merged through a process called accretion that gradually built Saturn's rocky core. The core accretion process required millions of years to build a solid foundation massive enough to capture significant amounts of hydrogen and helium. Theoretical models suggest that Saturn's core needed to reach approximately 1015 Earth masses before its gravitational field became strong enough to retain light gases against thermal motion and solar wind pressure. This critical mass threshold represents the boundary between terrestrial planet formation and gas giant formation. Computer simulations of early solar system dynamics reveal that Saturn's formation was influenced by the gravitational effects of Jupiter, which formed earlier and more rapidly in the inner regions of the gas giant zone. Jupiter's massive gravity scattered planetesimals throughout the outer solar system, creating a complex environment where Saturn had to compete with Jupiter for solid building material while avoiding gravitational disruption by its larger neighbor. The timing of Saturn's core formation proved crucial for determining the planet's final mass and composition. Saturn needed to complete its core accretion phase before the protoplanetary disk dispersed, which occurred approximately 3 to 10 million years after solar system formation. Planets that took longer to reach critical core mass were unable to capture substantial gaseous envelopes, explaining why Uranus and Neptune have much smaller hydrogen-helium atmospheres despite forming in similar regions. Once Saturn's core reached critical mass, the planet entered a runaway gas accretion phase where its growing gravitational field attracted hydrogen and helium at an accelerating rate. During this phase, Saturn's mass increased exponentially as the planet captured material from the surrounding nebula. The efficiency of this gas capture process determined Saturn's final mass and internal structure. The composition of Saturn's massive atmosphere reflects the chemical conditions that existed in the outer protoplanetary disk 4.6 billion years ago. The dominance of hydrogen and helium mirrors the cosmic abundance of elements, where hydrogen comprises roughly 75% and helium 24% of normal matter in the universe. The trace amounts of heavier elements found in Saturn's atmosphere provide clues about the planetesimals that were incorporated during core formation. Isotopic analysis of Saturn's atmospheric composition reveals that the planet incorporated materials from throughout the outer solar system, including water-rich objects from the asteroid belt and carbon-rich materials from the outer regions of the protoplanetary disk. This diverse source region explains the complex chemistry observed in Saturn's atmosphere and provides insights into the dynamic processes that operated during planetary formation. The thermal evolution of Saturn during formation played a crucial role in determining its final density structure. As the planet captured massive amounts of hydrogen and helium, gravitational potential energy converted to thermal energy, heating Saturn's interior to temperatures exceeding those found in stellar cores. This internal heating caused Saturn to expand to its current enormous size, while preventing the gravitational collapse that would have created a much denser object. The formation process that created Saturn's low density was not unique to our solar system. Observations of exoplanets around other stars reveal numerous gas giants with densities even lower than Saturn's, suggesting that the physical processes that created Saturn operate throughout the universe. Some exoplanets have been discovered with densities as low as 0.1 grams per cubic centimeter, making them even more buoyant than Saturn. The migration history of Saturn during formation may have influenced its final mass and density. Theoretical models suggest that Saturn may have migrated inward toward the Sun during its formation, then migrated outward to its current position through gravitational interactions with Jupiter and the remnants of the protoplanetary disk. This migration would have exposed Saturn to different temperature and density conditions that could have affected its final structure. The role of disk dispersal in Saturn's formation timeline explains why the planet achieved its current low density rather than continuing to accrete material until it became much more massive. Strong stellar winds from the young Sun, combined with photoevaporation caused by intense ultraviolet radiation, dispersed the protoplanetary disk after approximately 10 million years. This disk dispersal ended Saturn's gas accretion phase and determined its final mass. Recent theoretical work suggests that Saturn's formation may have involved multiple phases of core assembly, with the initial rocky core later supplemented by additional solid material delivered through continued planetesimal bombardment. This extended accretion process could explain some of the complex internal structure revealed by Cassini spacecraft measurements of Saturn's gravitational field. The formation of Saturn's atmosphere through nebula capture rather than outgassing from solid materials explains the planet's unusual atmospheric composition compared to terrestrial planets. Unlike Earth, where atmospheric components were released from rocks and ices through geological processes, Saturn's atmosphere represents a direct sample of the primordial solar nebula, preserved in the planet's massive envelope for billions of years. The efficiency of Saturn's formation process in creating a low-density planet depended on the precise balance between core growth rates, gas capture efficiency, and disk dispersal timescales. Small changes in any of these factors could have produced dramatically different outcomes, potentially creating a planet with density high enough to sink in water rather than float. The formation story of Saturn provides crucial insights into how planetary system architecture develops around other stars. The same physical processes that created Saturn's floating ability operate in exoplanetary systems, but different initial conditions can produce planets with vastly different properties. Understanding Saturn's formation helps astronomers predict what types of planets should exist around other stars. Dr. Hal Levison from the Southwest Research Institute reflects on Saturn's formation significance. Saturn's formation represents a successful experiment in creating a low-density planet through the precise timing of core accretion and gas capture. The planet's ability to float demonstrates how specific formation conditions can produce worlds with properties that seem impossible based on terrestrial experience. The formation story that created Saturn's floating ability demonstrates how planetary systems can produce enormous diversity in world types through variations in formation timing, composition, and environmental conditions. Saturn's existence as a floating planet results from the specific sequence of events that occurred in our outer solar system 4.6 billion years ago, creating one of the most unusual and beautiful worlds in our cosmic neighborhood. The formation processes that made Saturn light enough to float also explain why gas giant planets represent one of the most common types of worlds found around other stars, suggesting that floating planets may be widespread phenomena throughout the universe, wherever conditions allow gas giant formation to occur. Chapter 7. Comparison game: Saturn's status as the only planet in our solar system that could float in water becomes even more remarkable when compared to the densities of other worlds in our cosmic neighborhood. Each planet in our solar system tells a unique story about planetary formation and composition through its density, revealing why Saturn achieved such an unusual property, while other worlds remain dense enough to sink. Understanding these planetary comparisons illuminates the special conditions that created Saturn's floating ability. Jupiter, often considered Saturn's twin due to its similar composition of hydrogen and helium, has a density of 1.33 grams per cubic centimeter, nearly twice Saturn's density and heavy enough to sink in water. This density difference seems puzzling at first because Jupiter and Saturn formed from similar materials in the same region of the solar system. Yet Jupiter's larger mass creates gravitational compression effects that fundamentally alter the relationship between mass and volume. Jupiter contains 318 times Earth's mass compared to Saturn's 95 Earth masses, but Jupiter's volume is only 1,321 times Earth's volume compared to Saturn's 763 Earth volumes. Jupiter's stronger gravity compresses its hydrogen and helium more efficiently than Saturn's weaker gravitational field, creating higher internal densities throughout the planet's interior. This demonstrates how planetary mass profoundly affects internal structure, even when composition remains similar. Dr. Tristan Guillot from the Observatoire de la Côte d'Azur, who studies gas giant interiors, explains the mass-density relationship. Jupiter and Saturn show us that more massive doesn't necessarily mean larger when dealing with gas giants. Jupiter's stronger gravity compresses its materials more effectively, making it denser despite being composed of the same light elements as Saturn. The terrestrial planets provide stark contrast to Saturn's low density through their rocky and metallic compositions. Earth has a density of 5.52 grams per cubic centimeter, over 8 times denser than Saturn, due to its iron core and rocky mantle. Venus 5.24 grams per cubic centimeter, and Mercury 5.43 grams per cubic centimeter have similar densities because they're composed primarily of rock and metal, while Mars 3.93 grams per cubic centimeter has a lower density due to its smaller iron core and more porous rocky composition. These terrestrial planet densities reflect formation in the inner solar system, where high temperatures prevented ice formation and concentrated heavy elements like iron, silicon, and magnesium. The density differences between terrestrial planets and gas giants like Saturn illustrate how temperature gradients in the early solar system created distinct planetary populations with fundamentally different compositions. Uranus and Neptune, the ice giants of the outer solar system, have densities of 1.27 and 1.64 grams per cubic centimeter, respectively, both high enough to sink in water despite forming in the cold outer regions, where Saturn achieved its low density. These planets contain significant amounts of water, methane, and ammonia ices mixed with rock and metal, creating intermediate densities between terrestrial planets and gas giants. The higher densities of Uranus and Neptune compared to Saturn result from their different formation histories. These planets formed later in solar system evolution when much of the hydrogen and helium had already been incorporated into Jupiter and Saturn or blown away by solar winds. Without access to massive amounts of light elements, Uranus and Neptune could only capture modest atmospheric envelopes around their rocky and icy cores. Comparing Saturn to exoplanets discovered around other stars reveals that extremely low-density planets may be more common throughout the universe than once thought. Several exoplanets have been discovered with densities lower than Saturn's, including WASP-17b with a density of approximately 0.1 grams per cubic centimeter, and KELT-11b with a density of 0.18 grams per cubic centimeter. These super puffy exoplanets achieve such low densities through different mechanisms than Saturn. Many orbit very close to their host stars, where intense stellar radiation inflates their atmospheres to enormous sizes while adding relatively little mass. This thermal inflation creates planets with volumes much larger than Saturn's, while maintaining similar or smaller masses, resulting in even lower densities. The discovery of ultra-low-density exoplanets suggests that Saturn represents just one example of how planets can achieve floating ability. Different stellar environments and formation conditions can create worlds with densities ranging from gas-like to metallic, demonstrating the incredible diversity of planetary properties possible throughout the universe. Solar system moons provide additional perspective on Saturn's unusual density. Earth's moon has a density of 3.34 grams per cubic centimeter due to its rocky composition, while Saturn's largest moon, Titan, has a density of 1.88 grams per cubic centimeter because it contains substantial amounts of water ice mixed with rock. Even the least dense major moon in the solar system, Saturn's Enceladus at 1.61 grams per cubic centimeter, is still more than twice as dense as Saturn itself. This comparison reveals that solid objects in our solar system, regardless of their ice content, maintain densities significantly higher than Saturn's. The planet's floating ability results specifically from its gaseous composition and enormous volume, rather than from any property that could be achieved by solid worlds, no matter how ice-rich they might be. Asteroid densities provide further context for understanding Saturn's unusual properties. Most asteroids have densities between 2 and 8 grams per cubic centimeter, depending on their composition, with metallic asteroids reaching densities comparable to terrestrial planets. Even the most porous rubble pile asteroids maintain densities above 1.0 gram per cubic centimeter, demonstrating that only gaseous planets can achieve the low densities necessary for floating. Comets, composed primarily of water ice with rock and dust, have densities ranging from 0.4 to 1.2 grams per cubic centimeter. While some comets approach Saturn's density, their small sizes mean they contain negligible mass compared to planetary scales. Saturn's achievement lies in maintaining comet-like density across a volume 763 times larger than Earth, requiring entirely different physical mechanisms than those governing small icy bodies. The comparison game extends to brown dwarfs, failed stars that contain more mass than planets, but insufficient mass for sustained nuclear fusion. Brown dwarfs typically have densities between 1 and 10 grams per cubic centimeter, much higher than Saturn, despite being composed primarily of hydrogen and helium. The higher densities result from greater gravitational compression in these more massive objects. Recent theoretical work on planetary formation suggests that Saturn may represent the optimal mass for achieving minimum density in hydrogen-helium planets. Objects less massive than Saturn cannot capture massive gaseous envelopes, while objects more massive create stronger gravitational compression that increases density. Saturn may occupy a Goldilocks zone of planetary mass that maximizes volume while minimizing gravitational compression effects. The temperature comparison between planets also influences density relationships. Saturn's internal temperature of approximately 11,700 degrees Celsius creates thermal pressure that helps maintain the planet's expanded size against gravitational compression. Cooler gas giants would contract under their own gravity, increasing density and potentially losing their floating ability. Atmospheric composition comparisons reveal how trace elements can affect planetary properties despite representing tiny fractions of total mass. Saturn's atmosphere contains small amounts of methane, ammonia, and other compounds that influence thermal properties and chemical processes. But these trace constituents don't significantly affect the overall density calculation, dominated by hydrogen and helium. The magnetic field strength comparison provides another perspective on planetary properties. Saturn's magnetic field is about 1,000 times stronger than Earth's, but 20 times weaker than Jupiter's, reflecting the different internal structures and circulation patterns in these worlds. However, Magnetic field strength doesn't correlate directly with density, demonstrating that different physical properties can vary independently in planetary systems. Dr. Adam Burrows from Princeton University reflects on planetary density comparisons. Saturn occupies a unique position in planetary parameter space where its mass, composition, and thermal state combine to create the minimum possible density for a stable planetary object. This makes Saturn not just unusual in our solar system, but rare throughout the universe. The comparison game reveals Saturn as an extreme outlier in planetary density, achieved through a specific combination of mass, composition, and thermal state that creates the perfect conditions for a floating planet. While other worlds demonstrate how various factors influence planetary density, none achieve the precise balance of properties that makes Saturn the solar system's cosmic cork, floating serenely in the ocean of space. Understanding how Saturn compares to other worlds illuminates both the uniqueness of its floating ability and the physical principles that govern planetary properties throughout the universe, revealing why gas giants like Saturn represent some of the most fascinating and counterintuitive objects in cosmic science. Chapter 8. Waterworld Test. The ultimate test of Saturn's floating ability requires imagining one of the most extraordinary thought experiments in physics. What would actually happen if we could find an ocean large enough to hold Saturn and gently lower the giant planet into the water? This cosmic thought experiment reveals fascinating principles about buoyancy, planetary dynamics, and the behavior of matter on scales that challenge human imagination, while demonstrating why Saturn truly would float like the universe's largest beach ball. Archimedes' principle, discovered over 2,000 years ago, provides the fundamental physics governing Saturn's floating ability. Any object immersed in a fluid experiences an upward buoyant force equal to the weight of the fluid displaced by the object. Since Saturn's average density of 0.687 grams per cubic centimeter is less than water's density of 1.0 gram per cubic centimeter, Saturn would displace a volume of water weighing more than the planet's total mass, creating a net upward force that would keep Saturn afloat. The practical implementation of this thought experiment requires imagining an ocean of truly cosmic proportions. Saturn has a volume of 8.27 times 1,014 cubic kilometers, meaning the ocean would need to be significantly larger to accommodate the planet without overflowing. This ocean would need to be at least 200,000 kilometers in radius, roughly half the distance from Earth to the Moon, and several times deeper than Saturn's diameter to provide adequate buoyancy. Dr. Neil deGrasse Tyson from the American Museum of Natural History has calculated the specifications for such a cosmic ocean. The ocean needed to float Saturn would contain more water than exists in all the objects in our solar system combined. We're talking about a body of water with a mass comparable to a small star, held together by its own gravity to prevent it from dispersing into space. The gravitational dynamics of a Saturn floating ocean create fascinating complexities that extend far beyond simple buoyancy calculations. The ocean would need sufficient mass to maintain liquid water against the gravitational influence of Saturn itself, which would create tidal forces attempting to deform both the ocean and the planet. These tidal interactions would generate heat through friction, potentially affecting both the ocean temperature and Saturn's internal dynamics. When Saturn first contacted the cosmic ocean surface, several dramatic phenomena would occur simultaneously. The planet's atmospheric pressure would compress the water at the contact interface, creating shock waves that propagate through both the ocean and Saturn's atmosphere. The density difference between Saturn's outer atmosphere and liquid water would create complex mixing processes at the boundary layer. Saturn's atmospheric temperature of approximately -180 degrees Celsius would immediately begin freezing water at the contact interface, creating a layer of ice that might temporarily support Saturn's weight before the buoyant forces took effect. This ice formation would release latent heat, creating thermal gradients that could drive convective circulation in both the ocean and Saturn's lower atmosphere. The buoyancy calculation reveals that approximately 68.7% of Saturn's volume would remain submerged below the ocean's surface, with 31.3% floating above the waterline. This means that roughly one-third of Saturn would be visible above the cosmic ocean, creating a spectacular sight of a partially submerged gas giant planet with its polar regions and part of its equatorial band exposed to space. Saturn's ring system would create additional complications for the floating scenario. The rings, composed primarily of ice particles, would likely interact dramatically with the ocean surface. Ring particles in the lower regions might be captured by the ocean, while higher ring components would continue orbiting the partially submerged planet, creating a unique configuration where part of the ring system exists below the waterline. The rotational dynamics of floating Saturn would be profoundly affected by interaction with the ocean. Saturn's 10.7-hour rotation period would create currents and eddies in the surrounding water, while the ocean's resistance would gradually slow Saturn's rotation through tidal friction. This rotational coupling could eventually lead to synchronous rotation, where Saturn's rotational period matches its orbital motion around the ocean's center of mass. Tidal effects between Saturn and the cosmic ocean would be enormous, due to the close proximity and large masses involved. Saturn's gravity would create tides in the ocean with amplitudes measured in kilometers rather than meters, while the ocean's gravitational field would distort Saturn's shape even more dramatically than its current rotation-induced obliqueness. The thermal dynamics of the Saturn-ocean system would create complex heat transfer processes. Saturn radiates approximately 2.5 times more energy than it receives from the Sun, which would heat the surrounding ocean water. This heating could create convective circulation patterns in the ocean that transport heat away from Saturn, potentially affecting the planet's thermal evolution over long timescales. Chemical interactions between Saturn's atmosphere and the ocean water would produce fascinating chemistry at the interface boundary. Saturn's atmospheric methane and ammonia would dissolve into the water, creating complex chemical gradients and possibly supporting exotic biochemistry in the ocean regions closest to the planet. The magnetic field interactions between Saturn and the cosmic ocean would create electromagnetic phenomena unlike anything observed in nature. Saturn's magnetic field would induce electric currents in the conducting seawater, generating electromagnetic forces that could affect both Saturn's magnetic field configuration and the ocean's circulation patterns. Wave dynamics in the cosmic ocean would operate on scales completely unlike terrestrial ocean waves. Tidal waves generated by Saturn's gravitational influence could reach heights measured in hundreds of kilometers and travel across the ocean at velocities approaching several kilometers per second, creating dynamic conditions that would continuously reshape the ocean's surface topology. The long-term stability of floating Saturn would depend on complex orbital mechanics within the cosmic ocean system. Saturn would likely settle into a stable floating configuration where buoyant forces balance gravitational attractions, but perturbations could create oscillating motions that cause the planet to bob up and down like a massive cork over periods of days or weeks. Atmospheric dynamics of floating Saturn would be dramatically altered by interaction with the ocean's surface. The portion of Saturn's atmosphere below the waterline would be compressed by hydrostatic pressure from the overlying ocean, potentially triggering changes in atmospheric circulation that could propagate throughout the planet's entire atmospheric system. The visibility of floating Saturn would create one of the most spectacular sights imaginable in the universe. The exposed portion of the planet would show its characteristic banded structure and golden coloration, while the submerged regions would appear distorted by refraction through the ocean water, creating optical effects that would make Saturn appear even larger and more magnificent. Dr. Carolyn Porco, former imaging team leader for the Cassini mission, imagines the visual impact. Floating Saturn would represent the ultimate cosmic spectacle, a giant planet partially submerged in an ocean larger than most star systems, with its rings creating rainbow reflections on the water surface while its atmosphere generates clouds that tower above the cosmic waterline. The thought experiment of floating Saturn demonstrates that the planet's low density isn't just a theoretical curiosity, but would manifest in dramatic physical behavior if the necessary conditions could be created. While such a cosmic ocean could never exist in reality due to the enormous masses and gravitational forces involved, the physics governing Saturn's buoyancy operates according to the same principles that allow ships to float in Earth's oceans. The Water World test reveals that Saturn's floating ability represents a genuine physical property rather than just a mathematical calculation, demonstrating how the planet's unique combination of mass, volume, and composition creates real buoyant forces that would dominate gravitational attraction if an appropriately sized ocean could somehow be provided. Understanding the Water World test helps clarify why Saturn's low density makes it fundamentally different from other planets, showing how this seemingly abstract property would translate into dramatic observable behavior under the right conditions, confirming Saturn's status as the cosmic cork that could float in the ocean of space if such an ocean could exist.